Hello, everyone. So my name is Nikolai Atanasov. I'm the chair of the next session. So the next session is going to be about mapping, localization, and loop closure. There are 4 talks in this session, but unfortunately, the authors of the first paper couldn't make it due to visa issues. But we've prepared a voiceover for their video, so we're still going to play it. So the first paper is full-frame scene coordinate regression for image-based localization.
Image-based localization refers to estimating the 6th degree of freedom camera pose from a query image in a given scene. The representation of the scene depends on the approach used. It can be a database of images, a reconstructed 3D model, or a trained deep neural network. Here we only consider one image as input, although the image-based localization task can be extended by using a sequence of images as input. The input images are usually RGB only without depth information. Image-based localization is an important problem in computer vision and robotics. It is a key component of many computer vision applications such as navigating autonomous vehicles and mobile robots, pedestrian localization and navigation, and augmented reality. It can be operated in both indoor and outdoor environments using low-cost cameras without the setup and maintenance of infrastructure. Many conventional approaches are based on local features and efficient 2D to 3D matching. They use a reconstructed point cloud model, usually obtained from structure from motion, to represent the scene. Each point is associated with the image features from which it was triangulated. Localizing a new query image is solved by first finding a large set of matches between image features and points in the model via descriptor matching, and then using RSS to reject outlier matches and estimate the camera pose on inliers. With the advent of neural networks, previous work such as DZAC obtained the 2D-3D matches via scene coordinate regression. A patch-based coordinate CNN is trained using image patches of fixed size centered around pixels and the corresponding world coordinates of these pixels. At test time, patches of the same size are used as inputs of the coordinate CNN to generate 2D-3D correspondences. Similar to the conventional methods, a RSS-based scheme is performed to determine the final pose estimate. Obtaining a set of correspondences in a patch-based manner is very inefficient. Also, the fixed patch size limits the size of the receptive field, and thus limits the information that can be processed by the network. This makes it difficult for the coordinate CNN to predict accurate correspondences when the scene exhibits ambiguities, since the global context cannot be used by the network. Therefore, we propose to train a fully convolutional encoder-decoder CNN for regressing the scene coordinates for all pixels. However, the global image appearance is not as invariant to viewpoint changes as local appearance. Therefore, regressing the scene coordinates using more global information is prone to overfitting. We propose to use data augmentation to mitigate the problem. Data augmentation is needed to make the full-frame CNN to generalize to unseen views. In addition to the data augmentation in 2D image space, we also augment the data in 3D space. A simple and common way of doing data augmentation in the context of solving per-pixel tasks is to apply 2D-affine geometric transformations to the training images. The transformations we perform include translation, rotation, and scaling. We propose to augment data also in 3D space. Since we have the ground truth scene coordinate image, we can generate a local point cloud from that. We then add a small random perturbation to the ground truth pose to synthesize a new camera pose. Using the new camera pose, the point cloud, we project the points to the new camera plane to generate a new RGB image and its ground truth scene coordinate image. For the experiments, we use the 7 scenes dataset provided by Microsoft Research. The 7 scenes dataset is a widely used RGBD dataset which consists of 7 different indoor environments. With the proposed data augmentation, our method is able to achieve state-of-the-art results in localization on the 7 scenes dataset. We observe that training the full-frame coordinate CNN without data augmentation dramatically degenerates the localization performance on all the scenes. In addition to the direct measure of localization performance, We present the accuracy of the intermediate seam coordinate predictions. Our full-frame coordinate CNN is able to produce significantly better seam coordinate predictions. The results suggest that the global information could help the system to perform better in challenging scenarios. For example, our method is able to provide significantly better localization performance for stairs.
Thank you for your attention. So the next paper is efficient surface-based SLAM using 3D laser range data in urban environments. And the authors are Jens Beigli and Cyril Staknes. So Jens is going to present the paper.
Hello, my name is Jens Beigli, and I'm presenting today our work on 3D laser-based SLAM in urban environments, where we're using rotating laser range scanners to localize ourselves. So given such a sequence of point clouds shown here, we want to estimate the motion of the sensor in between, called odometry. However, odometry alone is affected by drift caused by small inaccuracies in the pose estimates, which accumulate to larger errors over time. Therefore, we also propose to use the surface map to find, when we revisit the area, to find loop closures and correct them as accordingly. Everything is driven by a surface-based map representation as shown here, where a circle corresponds to a small disk with a position, a normal, and a radius. Given that surface representation, we can now register a new scan, as shown here, where the sensor moved to the surface representation. For this, we first render a vertex in the normal map, image-based representation from the surface map, and use this then to projectively associate the point cloud with the image representation, which allows then to find correspondences for our point-to-plane ICP, which is then used to compute an update, which is then used to update the pose and then re-estimate the correspondences to find a novel update. Using the converged ICP estimate, we can then integrate the laser scan into the surface map. And as you can see, we add circles for beforehand unobserved areas, like in the lower right part, and also update already existing circles. For loop closure detection and verification, we also exploit our map representation. Suppose we have the following situation where we want to find for this golden scan the corresponding loop closure scan on the other side and find the transformation between these two scans. As we don't know how much we drifted in between, we have to consider multiple initializations for the ICP. But we now have to figure out what is the right registration in the end. For this, we could use such ICP residual, but as you can see, the residual would point to the wrong location because the minimum of the residual is on the wrong side of the street. We propose to use a map-based residual, which results in the correct minimum on the other side of the street and allows us, therefore, to correctly find the transformation between the two scans and integrate this into the post-graph optimization. And we can then correct the loop. Here, we evaluated our approach on the so-called kitty vision benchmark, where we show here the results of the projections of our poses estimated with our approach and project the point clouds from a bird's eye view. We show in the paper on state-of-the-art results on the training data, but achieved this with 20 times the speed. Together, we not achieve all the time real-time capability because the loop closure detection is currently somehow a little bit more involved, and that's maybe a future work point to improve this. In conclusion, here you can see a longer sequence of our approach working with multiple loop closures. And in conclusion, we are presenting a surface-based STEM approach producing globally consistent maps in large-scale environments. And despite its promising results, there are certain avenues for future work, like integration of IMU information, because Our approach has struggles when there's ambiguous motion, like in a dense traffic jam, where it's unable to distinguish if the car itself is moving or the surrounding is moving. So IMU would definitely help there. The other part we want to investigate is to integrate tracking information for dynamic objects, because dynamic objects usually cause outliers in our maps, which we can usually not remove from just one scan or multiple scans, and therefore we would like to integrate the tracking information here. And yeah, as you can see, this was the beginning, so we're coming back and we can close the loop again. Unfortunately, the URL is not completely visible, but it's also written in the paper. You can there find our data, but also our code, and you can try it yourself and reproduce our results. Thank you for your attention.
Okay, so the next paper is Near Optimal Budgeted Data Exchange for Distributed Loop Closure Detection. And the authors are Yulun Tian, Kasra Kasusi, Matthew Guimau, Jonathan Howe, and Jonathan Kelly. And Yulun is going to present the talk.
Hi, my name is Yulun Tian. I'm going to talk about our paper on budgeted data exchange for multi-robot systems. So in many multi-robot missions, the robots need to merge their local maps and do collaborative SLAM. In order to do this, they need to search for inter-robot loop closures between their past and current poses. Let me briefly tell you about how this is done. First, by roughly describing the places I've been to, the robots agree upon a set of potential loop closures, each associated with a correctness probability. Then, the robots need to collectively verify these potential matches, for example, using geometric verification. To do this, at least one robot must share its observation with the other one. For example, in this case, if Alice broadcasts her image, Bob and Eve will be able to verify these two potential matches. In reality, there will be many potential loop closures, and verifying all of them might not be possible when you have a hard resource constraint, like bandwidth in underwater scenarios or battery in the case of UAVs. Because verifying all potential loop closures is not an option, we need a way to prioritize the selection of potential loop closures to verify based on their expected utility or based on a good approximation of it. In order to do this, we introduce a value function f defined over the power set of all potential loop closures. Given any subset of potential matches L, for example, these three edges shown in blue, f will return the expected information gain after verifying L. Instead of restricting us to a single function, here we only make two broad assumptions. First, we assume f to be monotone, which is a natural assumption because more information is always beneficial. And also, we assume f to be submodular, which is a property already satisfied by many existing objectives in SLAM, including the d-optimality criterion. Ultimately, the choice of f depends on the application, but for more examples, please come to our poster session or refer to the full paper. Now that we have this objective function f, we can proceed to define the budgeted data exchange problem. Essentially, we're trying to select a subset of potential loop closures L to verify in order to maximize the expected information gain. However, our communication budget requires that the selected subset must be verifiable with at most B units of communication. Similar to the classical problem of submodular maximization, our problem is unfortunately NP hard. However, unlike the classical problems, even deciding feasibility is computationally infeasible in our case. That is, if you give me a budget B and the subset L, merely checking whether L can be verified by B units of communication is already NP complete when you have more than two robots. Therefore, it's clear that the best thing we can hope for are efficient approximation algorithms for this problem. And that is exactly what we do in this paper. Instead of coming up with a single algorithm, our main result, known as an approximation factor preserving reduction, allows us to have a factory of approximation algorithms for our problem. The core idea is that I can take any alpha approximation algorithm for the classical problem of monotone submodular maximization under a cardinality or knapsack constraint and convert it into an alpha approximation algorithm for our problem. For example, this table shows the resulting approximation factors achieved by converting the standard greedy algorithm. The resulting algorithms can handle various types of communication budgets, including when a single budget is imposed on the entire team, or multiple local budgets are imposed on individual robots. In addition, it can also handle cases with uniform or non-uniform observation size. In terms of experiments, we took the KITI dataset and divided it into multiple segments to simulate a collaborative SLAM scenario. On the x-axis of the right-hand side figure, we vary the communication budget B, and on the y-axis, we show the achieved objective value normalized by the maximum achievable value with infinite budget. So this makes the value always between 0 and 1. The black curve shows a random exchange policy. The blue curve shows our proposed algorithm, which is clearly much better than the random baseline. And finally, we also, for each problem instance, we also obtain an upper bound on the optimal value using an approach based on convex realization. This gives us a certificate on the performance of our proposed algorithm, which is typically much stronger than the worst case theoretical guarantee. And that's my talk. Thank you.
Okay, and the final talk for the session is lightweight, unsupervised deep loop closure. So it's everything you can wish for. And so the authors are Nathaniel Merrill and Guo Qian Huang, and Nate's going to present it.
Hello, everyone. I'm Nate Merrill, an undergraduate from the University of Delaware, here to present the approach to loop closure using a novel, lightweight, unsupervised deep neural network. This work is a collaboration with Paul Huang. Loop closure, or place recognition, is the ability for a robot to recognize revisited locations. This problem is difficult when the appearance of images differs greatly, but is essential to long-term SLAM, since loop closure allows a system to correct accumulated pose-estimation error. Recently, it has been discovered that intermediate features learned by deep convolutional neural networks are useful for place recognition. They are invariant to image appearance, so they make good descriptors for whole images or image regions. Unfortunately, these features are too large to match in real time without dimensionality reduction, which both hinders place recognition performance and is an expensive operation in itself for the large 65,000 element feature vectors extracted from AlexNet, which is depicted here. In response to this issue, a few recent works have trained networks specifically for place recognition, mapping images to a lower dimension internally with competitive accuracy. Most of these methods rely on supervised learning, with a training data set consisting of labeled triplets as shown here. Unfortunately, there is no publicly available data in this form, so it is difficult to obtain training data for these networks. In contrast, our unsupervised method allows for any images of any scene to be used in training. For each image in the training data set, we construct an image pair, performing random projective transformations to emulate viewpoint changes due to robot motion. This way, the network sees the same type of noise that it will encounter online. One image from each pair gets transformed into a hog descriptor. Hog provides a good geometric representation of a scene that is also invariant to illumination to a degree. We found the use of hog to be superior to purely using images or other various image description techniques in training. The other image from each pair becomes input into the network. The autoencoder is forced to reconstruct the hog descriptor of one image, given only the other. In the online phase, we drop all but the 3 convolution layers. The proposed network produces small 1064-dimensional descriptors. There are 3 main advantages to using our network over previous methods. First, the unsupervised aspect allows to obtain a large training data set, which makes for easy generalization. Second, the lightweight design allows for fast feature extraction. And finally, our descriptors are small enough for fast matching, but large enough to remain robust. Here we compare nearest neighbor searches for various methods to quantify accuracy. The pink line is from a standard denoising autoencoder, which is the same size as our network. The green is from AlexNet features reduced to the same size as ours. And the red is from the state-of-the-art DBO2. This curve is generated from a subset of the elderly data set. And our method, shown in blue, is shown to be superior here. This curve is generated from a subset of the Nordland, winter, and spring sequences. Again, our method is coming out on top. Our model is lightweight enough to outperform benchmark methods in a runtime comparison. We can extract features in under a millisecond on a cheap graphics card, and image matching is faster than that of DBO2 for any size search space. Here we use an a priori threshold from another data set to perform faster than real-time loop closure. This experiment was performed at 100 times real-time speed. Although a simple nearest neighbor search with a threshold and a temporal consistency check is used here, our model can also be incorporated into many off-the-shelf CompNet-based loop closure systems for an easy speedup with comparative accuracy. Finally, we note that we have released our code and pre-trained model to the public in the hopes of providing an out-of-the-box solution for real-time loop closure. It's provided here as a link as well as a QR code. If you have any questions or would like to see more results, please see me during the poster presentations. Feel free to contact me by email. Thank you for your time.
Thank you very much for your attention. I'd like to invite all the authors on stage now, and we have time for questions.
Question for Yulin? Tian?
Yes.
Sorry, Yulin. Sorry. I was wondering if you guys thought about perceptual aliasing because like the assumption that more information is always helpful doesn't carry over if you have perceptual aliasing, right? So.
That's a very good question. So in our paper right now, we assume that so in the final step of geometric verification, if the robots think that there is a potential loop closure, but it actually turns out to be a false positive, then it won't add that constraint to the post graph.
Cool.
Hi, I had a question for Yulin again. So loop closure detection is inherently a very stochastic problem because there are a lot of things that can happen. You talked about monotone submodularity. Just a clarification, are you thinking about the conventional setting of submodularity, or are you talking about adaptive submodularity for stochastic online settings? Because all the adaptive greedy is still bounded suboptimal. It's a different problem setting, and maybe you have to do more to use those results. So I just wanted to clarify that.
So right now, we consider the classical monotone submodular maximization problem. But so as I said in the presentation, so the original form of our optimization problem is not the same as the classical problem because the constraint is different. But our main result shows that we can have a approximation factor preserving reduction, which essentially reduce our problem to the classical problem, and hence the greedy algorithm will be able to have near optimal performance.
Okay, so just to clarify, that algorithm is not closed loop, like it's not online. It's not adaptive to changes in the environment, right?
Yeah. So right now, in our paper, we only did offline experiments.
Okay. Cool.
Yeah. I can ask a question for Jens. Is there anything specific in your method for LiDAR? Could you apply the same approach to an RGBD camera, for example? And what changes would you need to make?
So the idea is based on an RGBD approach, but specifically for LiDAR, we use a spherical projection of the point cloud. And we had to do some work on how to find out when circles are stable, because in outdoor environment, in a LiDAR setting, you have a fast-moving car and you have to integrate circles very, very fast. but you don't want to integrate dynamics. So for this we had to do some work. So, but basically it's based on the Elastic Fusion framework, so it was already applied to RGBD, so yeah.
We have time for a couple more questions. I can ask one more. I can ask Nate about your loop closure approach. So from what I understood, you currently are not taking temporal information as part of the training process or inside the network. Do you have any idea on how you might consider multiple hypotheses and propagate them over time?
Yes, that's a good question. In the online video that you saw, we were actually using a temporal consistency check, which is basically, you just need multiple positives in a row to determine loop closure. But no, in the training phase, we don't use any temporal information. Does that answer your question?
Yeah.
I guess.
All right, so if there are no more questions, let's thank our speakers again.